if we have a thin sheet of material or a shell, we can model it by a surface. So for example, if we had a metal sheet, this sheet technically might be three-dimensional with a thickness of like 0.1 millimeters, something very small, but we can model it by a mathematical surface which has zero thickness. Or if we had a bowl, this will have actually maybe some significant thickness, like this might have like half a centimeter of thickness, but if we're not like breaking into the bowl, we might not really care about that. So again, we could just model it as a surface that has zero width. Okay, so then just as for curves, we then have formulas for physically meaningful things like mass and moments. So it's sort of just a list of formulas. So the mass is going to be given by m is integral over s. So delta is density. Delta is a density function. I guess, yeah, adding a density is sort of what turns us from just a mathematical object into something representing a physical object. So the mass is the integral of the density over the surface. The first moments with respect to the coordinate planes are going to be m. yz is integral s x times delta d sigma, m xz is integral over s y delta d sigma, and m xy is integral over s z delta d sigma. And then the center of mass is x bar, y bar, z bar, where x bar is the moment with respect to the yz plane, myz over m. Y bar is m xz over m, and z bar is m xy over m. Maybe I'll try to delineate these a little bit, but I'm about to erase them anyway. So these are exactly the same types of formulas that we had for bodies in space or for curves. It's just now we're integrating over a surface and with respect to the area differential instead of with respect to like arc length. And then finally, we also have the second moments. So the formula for the moments of inertia about the coordinate axes are, so Ix is integral over s distance squared to the x-axis, so that's y squared plus z squared, density d sigma. Iy is integral over s x squared plus z squared, density d sigma. And Iz is integral over s x squared plus y squared, delta d sigma. And in general, for any line, you could define the inertia with respect to L as the integral over S of R squared delta d sigma, where R is the distance from the point X, Y, Z to the line L. So when L is the x-axis or the y-axis or the z-axis, that becomes these formulas here.